Isn't it nice? Target. Yeah. All right. It's not really new. It was from my house. I took it apart, brought it to school, put it back together.
You're gonna have that.
All right. Second derivative test. Go ahead and write the heading on the paper. What's showing through? Ah, that's not a blank sheet of paper. Well, hopefully I don't need it. All right. Second derivative test. All right. You guys stretch out your hands. Get them ready. Okay. A graph is concave up when f prime of x is increasing, which means that the second derivative is positive. A graph is concave up when f prime of x is increasing, which means that the second derivative is positive. So it's concave up on an interval. On an interval? Ooh, that's painful, huh? On an interval. All right. It is concave down. Sorry. There we go. I can read it. All right. It is concave down when f prime of x is decreasing. The graph. And I couldn't even say the graph, I'd say the function, f of x. F of x is concave up when f prime of x is increasing. F of x is concave down when f prime of x is decreasing, which means that the second derivative, why did I write a g? I'm not sure. F prime of double prime of x is less than 0 on an interval.
Can you say f prime prime, or do you have to say double prime?
You can say prime prime if you want people to make fun of you in college. A point of inflection.
I keep calling it f sharp. Which is ridiculous, but you know.
Oh man. A point of inflection is where the function changes concavity, which means that the second derivative is 0 there. Yeah.
It's like it relates to dentistry.
I know, I was going to say it makes me feel a little bit anxious. Got some PTSD with my dentist. All right. Yeah, that's what I was going to do. All right, so this right here is POI, that's the point of inflection. This part of the graph is concave down, because it's a U shape that's upside down. This part of the graph is concave up.
How does this test apply to functions that aren't polynomials?
It actually works for all sorts of functions, because functions are always curvy, right? Unless it's a piecewise function, they're always curvy. All functions, every single piece of them is either concave up or concave down. Well, so a linear function wouldn't have a second derivative, right? So this is dependent on it being able to have a second derivative.
A rational is the ones that are fractions.
Yeah, but even rational functions, like if you think about,
A radical one.
yeah, I'll draw a couple examples of those. So if we have a rational function, they look like this, right? This is concave up, this is concave down. The x value in between wouldn't really be a point of inflection, but it would be an x value that changed the inflection, asymptote of inflection. If you have a square root graph that looks like that, that's concave down. If you have a negative square root graph, then it looks like this, that's concave up. Yeah, it's just saying that the curve is like opens up or the curve opens down, basically, is kind of what you're saying when you do concavity. Here's another example. This would be a point of inflection. This is concave up, this is concave down. Cubic, yeah, negative, not an inverse, but a negative. Do we need to see more pictures of that, or does it kind of make sense? Okay. Yeah.
So wherever like
If you look at it sideways, it's a negative.
the curve is up,
Yeah.
then it's
If the curve could hold water, then it's concave up. And then if
It doesn't have to hold the water particularly well.
no,
But if it holds the water.
but if it holds any water, did that make it clear?
Yeah.
Okay. Yeah. Yeah, that's right.
I have a new worksheet.
Water damage on all the papers. All right, so here's an example problem. This example problem, we're going to be using the second derivative, but we are not using the second derivative test yet because I have not said anything about maximums and minimums. So if you guys recall from yesterday, the first derivative test and now the second derivative test, the only time you use those tests is to find extrema. Relative max, relative min. We're not doing that yet, so we're not using the test yet. But we are finding the second derivative, and we're going to use it to get some information. It's just not called the second derivative test yet. Okay? So the function we're going to look at is f of x equals x to the fourth minus 4x to the third plus 2. And what we're going to do is we're going to check to see where the second derivative is positive, and where the second derivative is negative, and where the second derivative is 0. And that's going to help us figure out if it's concave up, concave down, and where the points of inflection are. Okay? Yeah.
Are points of inflection also the same point as critical points?
It's not called, it would not be in the same place necessarily. It could be in the same place, but that would not be super common. So these are going to be different x values than what make the first derivative equal 0.
Yeah, that makes sense.
Yeah, so these are kind of like critical points for the second derivative, but we don't call them critical points because critical points are referring to the first derivative. So we're going to call it points of inflection.
I guess they're not, because if second derivative was also 0 always when the first derivative was 0, then L'Hopital's rule, or however you pronounce it, wouldn't be useful.
L'Hopital's?
L'Hopital's?
No, it's L'Hopital. It's L'Hopital. I'm sorry. I was making fun of you, which wasn't very nice, and I recorded myself, so that's terrible. All right. F prime of x.
Hi, YouTube.
Yeah. The first derivative is. Maybe if I move on really fast, nobody will notice. All right. The second derivative is. Okay, 24. X. Okay, so since what we are focused on is finding where the second derivative is greater than 0 and where it's less than 0 and where it equals 0, I'm going to go ahead and take my second derivative and set it equal to 0 and factor it. Okay, so 12x squared minus 24x equals 0. 12x, x minus 2. Okay, so the potential points of inflection are going to be at an x-coordinate of 0 and an x-coordinate of 2. It is only a point of inflection if it switches concavity. So if it was concave down and then it stayed concave down, that's not a point of inflection. You have to see when it switches. So that means we need to do a sign chart. Okay? So just like yesterday, right? We're thinking about it just like yesterday. All right.
what would that look like if it didn't switch?
Yeah, like the vertex of a quadratic could be a point of inflection. Well, you could solve it and find that it was like a point of inflection, but then when you look at it, you're like, oh, it's still concave up the whole time. Yeah. All right, so let's draw a picture. We got, well, not a picture, but a number line. We got 0 and 2. And what numbers do you want to test? -1, 1, and 3. So if I plug in a negative, then that's negative. Negative 12, right? Plug in -1. So negative times negative. Positive, no, because that'd give you a y coordinate, and I don't want a y coordinate. I want to know what sign the second derivative is. If I plug in 1, I get a positive times a negative, which is, and then if I plug in 3, positive times a positive, which is positive. Okay, so they did switch every time. So that means that x equals 0 is a location of the point of inflection, x equals 2 is the location of a point of inflection, okay? So for me, I'm going to go ahead and say point of inflection, I've got 2, x coordinate of 0, x coordinate of 2. How do I find the y coordinates of the points of inflection? Plug it into the original because the outputs of the original are going to give you y coordinates. Okay, so I'm going back to the original. F of 0 is 0 to the 4th minus 4 times 0 cubed plus 2, which is 2. If only they were always that easy. And then f of 2 is 2 to the 4th, 16, minus 4 times 8 plus 2. Okay, so there's your points of inflection. And then we can see that this says positive and positive, so those are the places where it's concave up. So concave up is going to be from negative infinity to 0 and 2 to infinity. And concave down is going to be from 0 to 2. Okay, to make this make more sense, let's go ahead and grab calculators and see what that looks like.
Make it today.
Yeah,
That's a worthy goal. Yeah, that's true. I was late.
Do you guys want to see a fun trick?
Yes.
Okay, so we know that the points of inflection are at 0 and 2. So I'm going to hit my window button. That means that the x values where the interesting things happen are at 0 and 2. So if I want to get a graph that's going to kind of like focus in on the stuff that are interesting to me, I could maybe say from an x value of like -1 to 3 or something. Does that sound reasonable? That's where all the interesting stuff happens. Now, if you hit the zoom button and go down to zoom fit, what zoom fit does is it takes the domain you plugged into the window. So my domain that I plugged into the window was from -1 to 3. It takes that domain and it makes the window make sense. It will change the y values automatically, but it does based off the domain. So anytime you've tried to do zoom fit and something funky happened, like it didn't work out, that's because your domain wasn't a good one for the problem. So if you can change the domain to be a good one for the problem, then the problem will fit on the screen. So it changed the y values for us. All right, so does it make sense that the graph is concave up from negative infinity to 0? Okay, does it make sense that the graph is concave down from 0 to 2? Yes, and then we can't really see past 2 because they didn't give us enough y coordinates to be able to see that. So I'm going to go ahead and change my y min to like -20 so that I can see that part where it goes concave up again. Maybe let's get some more. We'll go to 5. So when we get past 2, now we can see that it went concave up again. Does that make sense? Okay. So when we do these, the concavity and the point of inflection, you guys have never really found that information before. The purpose of us finding it is that now, this is like totally outside of like the math 3 stuff you used to do stuff on a calculator. Now I could, in theory, give you any equation and you could graph it by hand. Because you could potentially find the x-intercepts and y-intercepts. You've done that by hand for years, right? We've factored things and solved and whatever. And then between finding the increasing and decreasing intervals and finding the maxes and mins and finding the concavity, then you could sketch anything. That's like the idea. And I have many, many problems that I've tried this on that I will not assign you because I'm choosing to be nicer this year because I'm tired of students crying during this unit, okay? So, but that's the purpose. That's the purpose of what we're doing, is that when you find that information, it means that now you can do all of this stuff by hand that you used to think was only possible in a calculator. Does that make sense? Like most of us would be like, I don't know how to graph that by hand. I'm not plugging in all those points and trying to see where it changes like direction. But now that we have calculus, we can figure out where like the U shape changes and how to connect those different points we find. Does that make sense? We're kind of human calculators. Actually, yeah, calculators used to literally be people who calculated.
What
And so human calculator came first, technology calculator came second. Yeah. So when like calculating used to be a legit job in certain companies. Yeah, like NASA had calculators, like people who sat at desks and made calculations. Yeah. All right. So, oh my goodness. Okay. Now we are going to move on, and now we are actually doing the second derivative test. We are actually doing the second derivative test, which means what are we finding? Maxes and mins. So the second derivative test it means that we are officially moving on, and now we're actually going to find maxes and mins. So the second derivative test says if f double prime, so if the second derivative is continuous near C, and that C value I'm talking about is the critical number. And how do we find critical numbers?
First derivative is 0.
Yeah, so it's where the first derivative is 0, where the first derivative does not exist. So if the second derivative is continuous at the critical value, which we did still get from the first derivative, then we have two different situations. One is if f prime of C equals 0, so that's just saying it's a critical number again, and f double prime of C is positive, is greater than 0. Technically, it could equal undefined, but I think typically those undefined, oh no, I could. I'll have to look back at I think this is a textbook definition. I'll have to look back at the textbook and see if they mention anything about that. All right, so if f prime of C equals 0 and f double prime of C is positive, then f has a relative, should it be a max or a min? So greater than C means it's concave up.
Oh, min.
That would be a min.
Oh.
Right? Because it's concave up there. Okay. So if f prime of C equals 0 and f double prime of C is less than 0, then the function has a relative max at C. So before we were checking maximums and minimums to see where the increasing switched to decreasing and where the decreasing switched to increasing. Now we're saying if we know where those critical points are and you're concave up, then you must have a minimum. Or if you're concave down, then you must have a maximum. So it's two different ways of finding the exact same information. The reason that we need to know both of these tests, like you might pick one, you might be like, I'm a first derivative test person, I prefer that test. That's fine, until you get to a problem where they don't give you the first derivative. They only give you the critical points in the second derivative, and then all of a sudden you can't do the problem. Does that make sense? So the reason we have two tests is because we know in multiple choice problems, sometimes they only give us certain information to force us to do it the way they want us to do it, okay? So today, even though these problems could use the first derivative test to find your relative maxes and mins, we're going to choose to do the second derivative test because we're going to practice it. Right, right. And it would be like, but it's possible they could say there's a critical value here now, determine if that value is a max or a min, and then you would have to.
Oh, didn't we discuss that?
Yeah, didn't we discuss this yesterday?
Mr. Rice, can I hold the point of inception?
Sure.
Is there a third derivative test where we use the point of inception?
There is not. I'm so sorry. Okay. So what we're going to do now is we're going to go back to this problem, right? So I'm going to take that first derivative. So I have f prime of x. The first derivative was 4x to the third minus 12x squared. And what I want to do with that first derivative is I want to figure out what the critical numbers were. So how do I do that? Set it equal to 0. So 4x to the third minus 12x squared equals 0. How do I factor it? Squared, and then x minus 3. Okay. Okay, so x equals 0, x equals 3. All right. Now, we actually had a unique circumstance here where our point of inflection value, x equals 0. So we have a critical number at 0, we have a point of inflection. If it's a point of inflection, it's not going to be a relative max or min because it is where it switched concave up and concave down. So what would have happened on this is that if we did the first derivative test, we would have seen that it stayed, if we look at the graph, if we look at the graph, it was decreasing, it stayed decreasing.
And if we did the second derivative test using 0,
then we would know the point of inflection was 0 because we did the second derivative test. So if you were finding your maxes and mins using only the first derivative, then you would have done a sign chart and you would have seen negative stays negative.
yeah.
But if you were doing the second derivative test, you would already know that the point of inflection, you could do that and find that the point of inflection was 0 because you would have had to find the second derivative. Does that make sense? Or evaluate it using the second. It means that you would have had to find the second derivative. We're not done yet. So what we're going to do now is we're going to take this value of 3 and we're going to plug it into the second derivative. And we're going to see if it's positive or negative. So if I take the second derivative, f double prime of 3, then f double prime of 3 would be 12 times 3 times 3 minus 2. And is that positive or negative?
Usually we wouldn't already know to take off the 0,
Right, but we can do one from start to finish like this, but if you were doing this, to do the second derivative test, you have to have the second derivative. So you...
First prime. We've got a double prime. Yeah.
No, I was plugging it back in right here. I was plugging it back in right here.
Oh, we did the formula. Oh, okay.
I'm saying you could look at the second derivative and know. You could look at it. So like if I look at it right now, I'm like, oh yeah, that's definitely 0 is not going to be, it's going to be an issue there. Yeah. All right. The other thing is if you accidentally, let's say you didn't notice it was a point of inflection, then what's going to happen when you plug 0 into the second derivative? It's going to 0 out and you're going to be like, oh, that's not positive or negative. So that was a point of inflection. Yeah. Yeah. All right. So that doesn't give us anything, but is this a positive or a negative? Positive. Positive. So since f double prime of 3 is greater than 0, that means that the graph is which concavity? It is concave up at x equals 3, which means that x equals 3 is a relative minimum. So I'm going to say relative minimum at an x coordinate of 3. And then how do I find the y coordinate for the minimum? I go back to the original equation because the original equation is what gives me my y coordinates. And I plug in 3. And because I ran out of notebook paper, I'm just going to do it on here. Actually, negative 25. Look at that.
Is there any way to calculate the derivative backwards?
Yeah.
What do you mean?
So, is there any way, given f prime or given f prime prime,
Yes.
find f prime? Or
Yeah, that's integration.
That's
That's like the whole second half of calculus. Yeah. Okay. Do you guys want to see another example, or do you feel okay with that? Another example?
I feel okay. Yeah.
Okay. We could do one together on the book assignment.
I was even ambitious to say one girl is ahead.
All right. So number 13 is the first one we're doing. What is question 13? What's the equation? Plus 12x. Okay. What do the instructions say for number 13? Find the points of inflection and then look at concavity. Okay. So do we have to do the second derivative test? No. because we are not finding a relative max or min. So all we have to do is we have to find the second derivative, because that's how we find concavity and points of inflection. We're going to find the second derivative. We're going to set it equal to 0. We're going to do a sign chart. Okay? So what's the first derivative? Okay. What's the second derivative? Okay. Set it equal to 0, and that's going to help us find what? Not critical value. Point of inflection. Yeah, the important one. All right. What do I do next? Take out a 6. You can factor it. I always factor these because I think it's easier to do the sign chart when it's factored. The numbers are smaller, so it's nicer. All right, so x equals 2.
Yeah, you could set it to 6x equals 12.
Yep.
Yeah.
That's what we were just saying, is I prefer to have it factored because it's easier to plug a number in. Yeah, positive times positive or positive times negative, yeah. All right, so what's a number smaller than 2? 1. What's a number bigger than 2? 3. Ooh. All right, so 6 is always positive, right? So I've got a positive times 1 minus 2, negative. Okay, and then if I plug in 3, I've got a positive times 3 minus 2 is a positive. Okay. All right, so our point of inflection, and we know it's a point of inflection because they did switch. Our point of inflection has an x-coordinate of 2. We know that we do have a portion of the graph that's concave up and a portion of the graph that's concave down. Concave up would be 2 to infinity. So that's for the plus. Concave down would be negative infinity to 2. I need the y-coordinate of my point of inflection. So I'm going to take the original equation, plug in 2.
8 minus 24 plus 24 is 8. I got 8. Good job, Tristan.
All right. Next, let's look at 35. So we're going to get the different sets of instructions. I know it's annoying that we're going out of order, but we're going to go ahead and do it anyway. So what does the equation say for 35?
Find all the relative extrema.
Okay,
6x
so
minus x squared.
6x minus x squared. Okay. So it says to find all relative extrema. Okay. So what we need to do first, we're going to actually be using the second derivative test now, right? Because we're finding relative extrema. So first step, we have to find the critical points. Okay. So what do I do?
Derivative equal to 0, and it's 6 minus 2x.
Okay, so 6 minus 2x equals 0.
6 equals 2x.
I factored it. I just prefer to have it factored. So x equals 3. Okay, or Toby's way because I feel bad. Okay. All right. So now what do we have to do? So we have the critical number. We don't do a number line. That would be the first derivative test. We're doing the second derivative test. So to do the second derivative test, what derivative do you need? The second derivative. Let's find it. F double prime of x equals -2. That means that no matter what we try to plug in for x, the answer is always negative. That means that this graph is always concave down, which makes sense, right? You have a parabola that's upside down. Okay, so this is always concave down.
Any water.
So we're not stating concavity. We're stating if this is a max or a min. So if it's always concave down, then what is x equals 3? A max, which means that was the vertex, right? It's a parabola that's upside down. That must have been the vertex. Okay, so we're going to say that we have a relative max, and that relative max, you could say absolute max if you're feeling sassy about it. All right, so relative max at x equals 3. What are we going to do to find the y-coordinate? Plug it into the original.
Regular 18.
Yeah.
Minus 9, which is 9.
All right.
How'd you get the 36?
You got 6 squared.
I mean, sometimes when you make a mistake, you like go all the way with it, you know?
All I know is
All right. Does that make sense how we got relative max?
36 squared.
Okay. So we didn't have to worry about finding the concavity of everything else. We didn't have to worry about the number line because all we had to do is we had to see at that critical number what the concavity was. And we know that at all of them, it's always negative. And so, relative max. Okay. Make sense? All right. On the front of your sheet, I'm just going to help you read some of this stuff because we didn't do that in the notes we just did. So again, they're giving you a picture of the first derivative. Okay, so if we look at the notes that we took, we know that when the first derivative is increasing, that means that the second derivative is positive, which means that it's concave up. Okay, so what we need to look at on our graphs are we need to look and see where the derivative is increasing or decreasing. Does that make sense? Look at where the graph is increasing or decreasing. So right here, the graph of the derivative is decreasing, and so that means that the second derivative, or the slope of this graph, would be less than 0. You have a negative slope because the graph is going down, right? Negative slope because the graph is decreasing. So I'm going to say the slope of the derivative is negative. Okay? For this part, all of this, the slope of the derivative is positive. Okay? And then over here, the slope of the derivative is negative. Okay. So that means that these are your points of inflection. Does that make sense? Points of inflection. Yeah, it's nothing. Yeah. Yep, just nothing. Yeah. That would be one where if you were doing it by hand, you probably would have found that point, and then you would have been like, oh, it's concave up to concave up, and so then I X out that point and say it's not actually. Does that make sense?
Okay.
Yeah.
You don't. If it's concave up to concave up, you don't.
No. So that's why this one right here is not one of our answers. So point of inflection, we don't have enough information to find the y-coordinate, but we can say the x-coordinate is -2 and 2. But they didn't give us an original function, so we can't plug it in. Okay. And then we're going to say concave up happens -2 to 2. So where the derivative is increasing, that's where the second derivative is positive. And so that's where the second derivative tells us it's concave up. Yep. So concave down would be
-2,
okay.
2 all the way back.
Now, in the packet, the next thing that I give you are some charts. And the charts tell you positive, and they tell you negative, and they tell you where it's 0. And if you look at the charts, all 3 of the charts are labeled like slightly differently.
Woo!
Oh,
yeah.
All right, so here's one chart, and if you guys look at this, here's our first derivative chart and then our second derivative chart. So this is where you're going to be able to find the increasing and the decreasing and the critical value. This is where you're going to be able to find the concave up and concave down and find the point of inflection. And then you could use the first derivative test or the second derivative test to determine the relative max or min, okay? And notice it only says the location of the relative extrema and the location of the points of inflection because you can't find the y-coordinate. They only gave you, they didn't give you the actual function. They just gave you a list of outputs, okay? So we can make some conclusions, but we can't find the whole location, okay? I think this one is a little bit easier, so we're going to do one of the ones on the next page.
What happens if you make the domain equivalent to negative and positive infinity on your calculator?
It'd be super zoomed out.
1 over 0.00000.
Yeah, so if you were to do that, first of all, your calculator would probably like freeze and just stop graphing it. But normally the interesting stuff happens kind of in the middle of the graph. So what would happen is it would look like you didn't graph anything. You'd be so zoomed out that you wouldn't be able to see anything happening. Yeah. Yeah. All right. Which, we can do number 5 because I think number 5 is the hardest one to read. Okay. So if you look at the first derivative, what are the things that we need to keep in mind about the first derivative? What do we usually do first with the first derivative? We usually set it equal to 0, and then we say that the value where it equals 0 is a critical number. Okay, so if you look at that chart, that means that we have a critical number. Yeah, a critical number at -2. So I'm going to say my critical value or critical point or whatever you want to call it is -2. Okay. Then what else do we look for with the first derivative? Yeah, and they don't have any, right? They don't say the first derivative does not exist anywhere, so that's good. What else do we look for in the first derivative? We draw the sign chart. We plug in values, we see where it's negative, we see where it's positive. So they didn't say negative or positive, but they did give us the actual outputs. So if we have an output of 4, that's a positive output, what does that mean? Increasing. So I'm going to put increasing right next to this. Okay, they didn't tell us that it was just negative, but they gave us a negative value of 7. So what does that tell us? Decreasing. -3. -4. Decreasing. Okay, so we are going to say that this graph is increasing on what interval? So we're going to look back at the top. Okay, and we're going to say it's decreasing, and here we're going to look at all of these. -2 to infinity. Okay. Do you guys want to find the relative max or min now, or do you want to wait to do the second derivative? Because we have our critical point right here. Fight! I'm just kidding. All right. Okay, that's a good idea. All right, so now we're going to look at the second derivative. And when we look at the second derivative, what's the first thing we do? We see where it equals 0, and that number is a point of inflection. And so that means our point of inflection is at x equals 3. Okay. And then we would make the sign chart, and then we would plug numbers in and see if our answers are positive or negative. And the positive or negative answers would tell us what? Concave up or concave down. So this is negative, so that's down. Concave down, -4. Concave down, -7. Concave down, +8. Concave up. Okay, so this graph is concave down for all of these. And then it's concave up. Okay, so to use the second derivative test to determine if we have a relative max or min, then we have to say f double prime of -2. We have to know what the sign is. Okay, so just looking at your packet, we have to know f double prime of -2. And if you look at your packet, it says the f double prime of -2 equals -4. So that means that f double prime of -2 is less than 0, which means that it is concave down, which means it's a relative max, yeah. So that means relative max at x equals -2, but we don't have enough information to find the y coordinate, so that's all we can say.
Realize that if you're concave up or concave down, you can ask it.
It's a real pumpkin.